Okay, great. So my project is titled Learning Sparse Interpretable Features in Vision Transformers, which means I'm one of the many people working on sparse autoencoders. So motivation for this project, as we move towards AGI in the future, I think systems will become increasingly multimodal. And so I think it's important that our mech-interp methods are future-proof and will generalize these models. I also think multimodality will increase capabilities because of transfer learning between different modalities. There's a bit of a heuristic argument, but I think humans, for example, gain a lot of intuition about how the world works through our vision. So that's kind of the reason for this in the future, why I'm doing this for theory of change. And also, can these mechanistic interpretability methods that have been developed in language be used to improve state-of-the-art interpretability for vision models? So my project in particular is training a sparse autoencoder on a clip vision transformer. I'll assume knowledge of SEs. I'll briefly go over vision transformers and what clip is for those who don't know. So a vision transformer is an architecture for vision models, different to convolutional models, in which you start off with an image and break it down into a grid of image patches, typically 16 by 16, and then you flatten the result into a 16 squared 256 set of tokens, each of about size 3 by 14 by 14. You then flatten each of the image patches into a 3 times 14 times 14 vector, and then embed that into some dimension d with a linear map. So there's no locality in this model, unlike a convolutional network. The model has to learn all of the spatial relationship between pixels. So it's surprising that they work. We then have an additional token beyond the 16 squared, which is the class token. And then you have full attention across the whole image. So it's a BERT-style model. The class token then generates, after the final layer, an embedding which represents the information about the whole image. So clip models. You train, so CLIP stands for Contrastive Language Image Pre-training. So you take pairs of images and text associated to the image, which can be beyond just labels of the image. They can be paragraph descriptions of everything in the image. So they contain much richer details than typical training with labels. So it's like pre-training in the full sense, and you take a batch of the text and images, and the model tries to work out which text associated to which images. And the complexity of the images is then absorbed into the sort of embeddings of the text, and vice versa. So you get this transfer learning between the two. And in fact, clip models are the basis of text-to-image generation. I assume, although I'm not sure, OpenAI's DALL-E and Sora also use something like this. But certainly, Stable Diffusion uses the Hugging Face open source clip text part. So it conditions on text to generate your diffusion images. And in fact, it's actually conditioning on the clip embeddings because you get this sort of like transfer learning, which allows you to generate realistic images. So specifically, I'm using OpenAI ClipVit large patch 14. It's the largest one from the original OpenAI model, and that is the one that's used in Stable Diffusion. And in fact, it's, I think, the fourth most downloaded model on Hugging Face with about 50 million downloads a month. I think GPT-2 has something like, I can't remember, something like 5 million. So it's like 10 times larger. So this is like more popular. So it seems important that this is used in the real world to maybe have some better understanding and see if we can gain insights from mechanistic interpretability. I'll move on to my results. Trained on ImageNet. The original CLIP model is trained on a much broader set of data, but it's too big for me to train on. I'm training an SE on the residual stream of layer index -2, so 2 from the end, on the class token. So it represents the whole image. We then want to visualize what the SE has learned. So I do this with highest activating images, and also some traditional feature visualization. So maybe there are just like spurious correlations as a result of using ImageNet, and actually the highest activating examples aren't reflecting the reality of what the SE has learned. And then in the future, I want to use Stable Diffusion, so conditioning the Stable Diffusion not on the text, but on the SE embedding itself to generate a representation of the image. I haven't got that to work. It's slightly more difficult than I'd anticipated. And also automated text explanations. This is a multimodal system, so we should be able to use that, the model itself, to generate explanations of the SE features. Again, I haven't quite got that working yet. This is the training run on weights and biases. The important thing to look at is the final one. We have an L0, which is the number of SE features that activate on any given image. It's about 24. That seems quite high, but in reality, there are only about 5 that strongly activate typically on an image. The others are kind of like epsilon activations. So this shows that the model that I've trained is sparse. And it seems to work. So the next 5 examples, I'm going to spend a lot of this presentation just showing you examples of SE neurons to give you a sense of what it's learned. The next, I think, 5 or 6 maybe are just random, so I'm not cherry picking these. So this is like orcas in a display in a swimming pool. This is dogs, but specifically gun dogs. So dogs with pheasants in their mouths. When I trained actually on or evaluated on more images, it had dogs with guns next to them. So these are just random neurons. This is like old tech, I think. It's maybe slightly mixed. There's like a joystick thing in there too. This is like crustaceans in food. So lobsters, crabs, that sort of thing. This is a yurt. This is a border terrier neuron. So it's learned a lot of the, but I think because I'm training on ImageNet, the SE has learned all of the ImageNet classes, the 1,000 ImageNet classes. So in some sense, you might say, well, it's actually not doing anything very profound. It's just replicating the classes in the data. And I think that's probably true on most of these images. This one's a border terrier one. I think it's be interesting to look at feature splitting if we constrain the encoder dimension, seeing how like different dog species split. So those are like random examples. Here are some more interesting ones. So I won't go through all of the boring image ones. This one activates, other than this image here, but if you look beyond the top 9, actually all of them activate on twin dogs. So dogs where they're side by side of the identical species. In fact, if you look at the bottom left here, these dogs are actually wearing the same collar too. This one's a bank robber neuron. So balaclavas, CCTV images of a bank robber. And then also, if you look beyond the first 10, there's also one of an ATM being smashed open. Sorry about this. There we go. This is a pixelation neuron. I think that's quite interesting. This is, again, going beyond ImageNet classes. And it's interesting that the model learns that representation, but it makes sense because the way you process the data, okay, I'll hurry up, is different. This is a repetition neuron, so when there are lots of examples of the same object in the image, this one fires. This is like chromatic aberration in the image, so you can see like this like weird RGB splitting. This is a watermarking with websites. This is watermarking in Chinese scripts. This is like where you have separate images within the things, or like blocks of things. I mean, this one's a long neck neuron, so emus, llamas, flamingos. I mean, I can go through. There are tons of examples. All of them are quite interesting to look at. This one's like objects that are signed, hand signed. Like some old modeling, I'm not quite sure, but in black and white. This one's really abstract. So I think this one is a size comparison neuron. So if you look at the bottom left is like a mushroom with a coin in the bottom, used to illustrate like a comparison of size. It's like a crayfish and a ruler, a centipede and a coin. The big fish in the middle using arm span as comparison. Coke can, a ruler. I don't quite know what's going on with these sea cucumbers. I'll leave that up to you to work that out. Yeah, and there are lots of location and culture neurons. So this is activating on these pillars. I think that is an ImageNet class, but also you see it's activating on a plane with the word Cairo on, and pharaohs, and then some like Middle Eastern dress. This one I think is maybe Vietnam. It's got like pho or pho, however you say it. Australia, Japan, Africa, etc., etc. I wanted to do an interactive game with the audience, but I can't do that because I couldn't use the app. So this here is at inference time. I'm passing an image through. We're looking at the SE activations and seeing if we can reconstruct the input image. So there are 3 high activating examples here, SE neurons. Highest one is like a monkey thing. Second highest is animals with like pups or babies. It's like swans, tiger, and the pups, etc., etc. Monkeys, and then pixelation as the 4th highest. Take a guess what it is. It was a monkey with a baby, and it's pixelated. So this is kind of remarkable if you think we're just given the activation vector on the residual stream, just a list of numbers up until now, completely black box on one token, one layer, and we can completely reconstruct all of the semantic meaning in the input image. I think that kind of shows the power of SAEs. Finally, with feature visualization, we need to like check that the SE features are actually learning what we think they have learned. So this is like the border terrier neuron, but maybe there's like spurious correlations. If you look here, you can see the sort of like shape of the border terrier's head in the feature visualization. Turns out that feature visualization is actually quite difficult to do, but this just goes to show that actually the SE has learnt what we think it has learned. And having had a border terrier myself, I can recognize those, I think at least, as that breed of dog. Birds on branches. And so here you can see like a bird with a branch underneath. Same as like this one here is like a bird, and then a branch coming down here, and then like foliage in the background. Mushrooms, again, you can see the mushrooms on the imprint of the feature visualization. Aqueducts, again, you can see the like arches in the images. Tennis, I think here this is like ATP. It's a clip model, so it should recognize text. That's like the International Tennis Association. There's like a racket neuron here. Likewise, there's like racket neurons here, and then I think these are like tennis balls. You can see some tennis players here. He's wearing like an armband, which tennis players typically wear. Yeah, so it seems to work quite well. Future work, yeah, I mean, I can go over it briefly, but like getting automated text explanations, stable diffusion, automating the scoring of the images, and then train across more layers, expand it across bigger data sets. So big thanks to Joseph. I'm building off his work, his code base. Also Jessica, my mentor, and Arush from Leap Labs to help me get these feature visualizations working, and also to my stream and Laura as well, my research manager. Any questions? I think I've got like 10 seconds, so. Okay.
How are you generating those toward the end? You were showing the sort of deep dreamish feature visualizations. How are you getting those?
Those are from Leap's API. So this is all done behind the screens. There's constraining. So I think this is difficult to do. Often these artificial images, which are explicitly trained to maximize the activation of an SAE neuron, actually don't activate the neuron as strongly as the natural images. And I think that's because this is kind of an adversarial attack, and VITs seem to be very adversarially robust. So I think it's very difficult to get signal into these images until you constrain it to these like real-world natural objects before it will actually maximize the neuron. But yeah, I haven't done this myself. This is thanks to Leap Labs, so thanks to them. But yeah.
Have you tried checking like training the SEs on earlier layers to see what how different they are, what they look like?
So I want to do that, but I think a recent paper has shown that if you train on the class token, the information typically is moved to the class token from the image patches in the last few layers of the image by those attention heads. I think if I were to train on earlier layers, I'd want to get this working on image patches, train SEs on image patches. That's a future direction I want to look at.